Yep.
Go for it?
Let's go, yeah.
All right. Hi, welcome to the fourth episode of the Neural Information Retrieval Podcast. I am Sergi Castella, your co-host from Zeta Alpha, and with me I have...
Andrew Yates, assistant professor at University of Amsterdam.
And today we're here to talk about this paper called Transformer Memory as a Differentiable Search Index. I'm pretty excited because I feel this. I don't know. I had a lot of fun reading it. I felt like it went a bit in a different direction than what I'm used to checking out. Do you want to say a couple of words about what this paper is about and why you think it's interesting to discuss it?
Yeah, no, it's to me a very interesting paper just because it does everything differently. So I guess we'll get into the details of exactly what this means, but it essentially proposes a new paradigm for indexing and retrieving documents using these large language models.
Mm-hmm. Yeah, so this paper is authored by Yi Tay and colleagues from Google Research. And that said, I think we can just get into the gist of the paper. What do they do? If we can have a 2 minutes summary or abstract.
Yeah. So what they'll compare against, and I guess a more normal way or a previously normal way to do things, you take a query, you take a document, you encode them into dense vectors, and then you score queries and documents by taking their inner product. So you can use like a maximum inner product search, some approximation in order to quickly find the documents closest to a query. Mm-hmm. This is the normal approach. And
so basically you basically have some explicit distance calculation between query and document.
Exactly. So you fix the distance calculation, you're storing these vectors in some way in this approximate nearest neighbor index, and your job is to produce the vectors such that they work well with this fixed calculation. What they're doing here is basically collapsing all of that into a single model. So they have a large transformer model that they try to index the documents in, they say. So this transformer model somehow holds the documents, and then they ask the transformer model to identify the documents relevant to a query. So there's no separate scoring step, there's no separate index, there's no approximate nearest neighbor search. All you have is one transformer model that somehow handles all of this. So that's why I say it's quite different.
Yeah. No, I think that's super interesting. So what I read about this thing, about the model kind of outputting document IDs directly without using the search index, the thing that it reminded me was this thing that, so there's been some research in the past couple of years that looks into what sort of weird things language models memorize. I think that it's something that's become quite famous, like some GPT something, when prompted in some way, will reveal an address of someone that just appeared a couple of times in the training corpus, which is a really surprising thing to many. And also, I think it's framed often from this negative perspective of like, this is a privacy problem. You should be really careful in how you train language models because they might memorize sensitive information. And I've seen it also framed in this also sort of negative way of if language models, if all they do is sort of memorize things, they don't quote unquote understand or something like that. And I feel like this paper sort of flips that around and say, okay, if language models memorize really weird and weirdly precise things that don't make any sense, can you sort of use that to your advantage to memorize a lot of things? And it seems like it sort of works, and I feel it's very interesting.
Yeah, no, it's a really interesting way to take advantage of this behavior, I think. And they do memorize, I guess, but when we think of them as memorizing, they have to combine things they've memorized also, right? So really this, in some cases, this is probably leading to the good performance we see. Some combination of memorizing things and understanding how to put them together, where understanding is probably in quotes there.
Yeah, understanding is very ill-defined concept.
Yeah, especially in this area, yeah.
All right, so shall we get a bit into the previous related work, because there's this work called Autoregressive entity linking that the authors mention as a sort of source of inspiration, and I think it's really useful to understand a bit where this approach comes from. Can you give us like 5 cents about that?
Yeah, so in this autoregressive entity linking, what they do is the goal is to link entities. So you see some text with the service form of an entity. So President Obama did XYZ, and your goal is to identify the entity in that sentence. So here the entity is something like Barack Obama. So this method would take that sentence as input, and then its output would be the canonical name of the entity that appeared in that sentence. So, Barack Obama, Amsterdam, whatever, some canonical representation of the entity as its output. So I guess if you think back about memorization, you can kind of imagine how this might work. So if you've seen, if you haven't seen an example during training, there might still be some patterns that can be used to figure out the canonical name. So if you have, Chelsea Football Club, and then there's Manchester, another football club, that hasn't been seen during training, you can imagine switching the place names and keeping the rest of that canonical name.
So in that case, the model would sort of be able to figure out canonical names of things, even if the model has never seen that entity before, right? Like it's like, okay, if Chelsea is in the context of football, in like soccer or context, this is probably like a football club. So like it figures out like a way to arrange that.
Yeah, the way I think of it is it's doing some implicit entity typing with the sentence. So it guesses this entity is a football club or a person or something, and then maybe some usage of patterns in order to come up with, the right canonical name.
Yeah, but
there.
The interesting part is that it's all implicit, right? There's no component that is like type, like it tries to classify that. It is all like autoregressive generation, which is all implicit memory within the neural network, which is also what's happening in this a transformer as a differentiable search index.
Exactly. So, but actually one more explicit part of the autoregressive entity linking that might be relevant is, I guess, when they decode the entity names, when they're predicting them, they're restricting their beam search to, I believe, valid entity names based on some corpus. So they're bringing in some, I guess, very slight notion of an index there. Whereas here, I don't think I'm not... It depends what they're doing. Maybe we shouldn't relate it back to that yet. There's some
it depends on the document ID representation.
Exactly. Right? Yeah. Skipping ahead.
Okay, that said, so we have a bit of the problem setting, right? So we're doing retrieval, and instead of doing some distance calculation between a query and a document, we have this transformer model that you feed it a query, and it just outputs a document ID, or not a document ID, but like a list of document ID with some likelihood associated, and then you can have a list of that, right? So basically, during retrieval, you're not using the quote-unquote index at any point. All right, so I think that it would be useful, at least for me, to define what an index is in a broad sense. Like, what are we talking about when we talk about an index in a conventional sense?
Yeah, in the IR sense, an index is some data structure that you store documents in that also lets you quickly identify the documents relevant to a query. So I briefly mentioned like approximate nearest neighbor search when we're talking about the bioencoders at the beginning. So here, this is some index where you give it a query representation, and it can quickly find approximately the closest document representation to that query representation.
Okay.
So some data structure given a query, it helps you find documents.
Okay. And in the context of this paper, they use this differentiable search index. Can you like give an explanation of why that term makes sense, or why they call it this? Yeah,
how I understand the term is they're essentially saying they're storing documents in the transformer, and so now the transformer becomes an index in some sense. And of course, the transformer is differentiable because this is how it's trained, so now the index is also differentiable. So I guess it's saying the model weights themselves are where the documents are now stored in some sense.
I think that they also use at some point the term like associative memory, or use this as at least a source, as some sort of inspiration to say like there's some level of associative memory within the transformer that maps queries into these document IDs, which I guess, I don't know to what degree this is relevant, but I feel it kind of tries to tie it a little bit to how maybe humans think about stuff and like recall things based on questions asked and context and all of this. Or do you see this like link here, or do you think it's just like...
Yeah, I mean, I don't think the documents are all stored discretely in this transformer, to put it that way. Right, so if you think of the NN index, you have a separate entry for every document. They're probably all entangled and mixed together in some way. It's really an implicit index, though, so it's hard for me to imagine what can possibly be going on. But I think, the associative memory, there's relations between things are being stored and somehow used.
Yeah, no, I mean, like you said, it's so hard to wrap your head around what is going on in there. And I mean, I feel this paper is only scratching the surface on what can be done in this sort of paradigm of retrieval, so to speak. So there's probably going to be a lot more works that explore some qualitative properties of these models and all of this. That's really interesting. Okay, I think that it would be useful before we get into the description of the method, if we, you kind of have already mentioned this, but you can maybe define what indexing and what the indexing and the retrieval stages mean in this context. We're talking in like page 4, top right of the paper. They have a couple of definitions that I think that are useful conceptually.
So their definition of indexing here, I guess it's teaching the model to associate a document ID with a document. So normally with a data structure, this is easy to do because you made the data structure and you have some way to use the doc ID to point to some part of that, right? But here they have to actually teach the model that here's a document and that corresponds to doc ID 123, for example. They come up with other type of doc IDs also, which we'll discuss. But this is the indexing step. And then retrieval is using those doc IDs in response to a query. So you have some query, how many people live in Amsterdam, and then it should return a doc ID that has the answer to this query. So you see they're reusing the doc IDs that they've stored, so to speak. So you're doing something like mapping from query to document to doc ID and then returning that doc ID.
So the mapping of indexing and retrieval is roughly 1-to-1 to training and inference in what you would call like conventional machine learning, right?
Yes, I guess with the caveat that they also need to train how to do the retrieval. So they look at different ways to train it, right? So they have to index in some way. So these are examples of doc ID and document text. And then in this training phase, they also may be using some queries to try to learn the retrieval task, to learn how to map between a query to a doc ID. And then at inference time, of course, they're just doing this task where they receive a query as input and they output a document ID.
Oh yeah, so the indexing phase sort of includes both sort of unsupervised pre-training and supervised, like using annotated pairs of queries and relevant documents to
yeah, exactly, or at least the non-zero shot case. They look at it both ways, which I think we'll get into.
Yeah, absolutely. That said, I think that where we can start is in the representation learning side of things. So they talk about learning representation for documents in the indexing stage. So pretty much like what part of a document you use, like you just kind of get bags of words, you just get like a part of a document, like truncated. And then we'll look into the ways they try to represent IDs for this document. So shall we start with documents? Yeah,
so like you said, for indexing, they have to somehow represent the documents and the document IDs. So this is the step where, they're feeding a document ID and they're feeding a document, and they want the model to remember this association. So the easy ones are, feed in the document, model should predict the doc ID, or the reverse of that. Feed in the doc ID, model should predict the document.
As in, like, autoregressively generate the content of the document?
Yeah, the entire content of the document. Okay. So the former works better in experiments, we'll see later. So this mapping from document text to token only.
Okay.
And then the other possibilities they try are, I think they call it bidirectional. So it's just both of these, along with some information to indicate which the model should be doing for a given example. And then I believe they call it span corruption, which is including the document ID in the document somehow. I don't know if they stated exactly what the formatting is here, but you can imagine some header that indicates what the document ID is, and then the rest of the document follows. Yeah, I believe it's something like this, with the document ID hidden in that header, and then they try to predict it.
By the way, what Andrew just mentioned of predicting doc ID based on content or predicting content based on doc ID, they call this input to target and target to input, right? Where target is the doc ID.
Right.
So that's just a terminology thing. All right. So you just mentioned actually we'll see that later. The one that works best is this input to target, right? Well, I don't know if it makes sense. We can ask that.
Yeah, maybe we think about it later. The first option is how we get the model to remember this document ID to document association. And then this option, the representation, is what we want the model to remember. So how we represent the document that we want the model to store. So the simplest thing to do here is just to take the first, they call them L tokens. So you have a document, you say, I'll take the first 32 tokens is their common setting. And then you want to store these 32 tokens in the index in a way that associates them with the right doc ID. But this they call direct indexing. They also look at other ways to do it. So like set indexing, they treat the terms as a set rather than trying to maintain the order. I think they also do some deduplication and stop word removal with this approach. So it's a set of terms minus the stop word terms. And then the other approach kind of feels like trying to go beyond this issue of only looking at the first 32 tokens. So they come up with different chunks of the document and try to store them. So I think they randomly take 32 tokens from anywhere in the document, for example, and try to index this. So you're not limited to the first tokens.
So you mentioned that in direct indexing, this just getting the first L tokens of a document. You mentioned that in practice, they use 32 tokens. That sounds like a pretty short context in, like modern transformers and stuff. Do you have any idea why they would only do that? And because do documents contain? Well, I mean, they're using the natural questions dataset, so those documents are pretty short, right?
Yeah. So I think the documents are Wikipedia passages. Okay. If I understand right. Yeah, so the documents are pretty short, and I assume at some point there will be capacity issues, right? You can't scale this up to 500 tokens and have a very small transformer and hope to be storing a lot of documents. So I don't know how all these things interact, but maybe they kind of want to establish that this paradigm can work without, having a massive model that's somehow capable of remembering very large documents.
No, absolutely. But I still think it's kind of interesting to kind of anchor that into the actual number, because when you talk about the first L tokens, in my head I would imagine like 500 or something. It's actually 32, which is like a tweet or something.
I think later they go up to like 128, which we'll see, and this does hurt performance, which makes me think of the capacity issues. All
right, now we do jump to the document ID representations, right?
Right. So we said they were storing document IDs, but we didn't say what a document ID actually is. So the most common thing elsewhere, I think they call unstructured atomic identifiers, which is just assigning a number to every document. This is document 1, next is document 2, etc. The downs...
So there's one token per document.
Right. One token,
it's like having a dictionary that is as big as the corpus, right?
Exactly.
Or like a hyper large classification layer.
Right. So say they have some vocab, say 30,000 terms. This is common with WordPress models. This vocab needs to increase by the number of documents they want to store. So if you have 100,000 document IDs to store, now you have 130,000 vocab tokens, because 100,000 of these are just unique document IDs, which means your output layer needs to grow a lot also, because you need a separate dimension for every document ID.
Yeah. Okay. Yeah, absolutely. Then what else we have?
Yeah, so we also have what they call naively structured string identifiers. So this is creating document IDs in the same way, but not treating them as single tokens. So if you have a document ID 123, this could either be a single token 123, or it could be 3 tokens, right? The token 1, the token 2, the token 3. And so that's what they're doing here. They're splitting that identifier into separate tokens that they can predict one after the other.
But we're still talking about these few tokens is just like a string of numbers, so it's not semantically relevant or anything.
Right.
Right. So my question is like the fact that the first 3 numbers are like 4, 7, 6 tells you nothing about the next 3 numbers. So in some way, it seems like a not the reason, like strange thing to try out, right?
Yeah, so from that perspective, it's strange. But if you think about what's going on with efficiency, I think that's why they try it. So they're not increasing the size of the vocabulary by the same amount, right? Which is quite expensive. I think this is why they're interested.
I think they mentioned later that there's like some stability problems, right, when training this so large last layer with a super large vocabulary. All right. And then we finally have these semantically structured identifiers.
So this, as the name says, is actually semantically structured, like you were complaining about with the last one. So basically, they're doing some hierarchical clustering here, right? So they represent the documents using something like, a vector from a document encoder, like you would use in the biencoder retrieval world, clustering these, and then the ID is like the cluster path. Right. So, you start with one cluster of the documents and you break this up into smaller clusters and you keep going. Every time you move to a new cluster, this adds a digit to your document ID, basically. So they're meaningful in some way.
Yeah, absolutely. And they actually, if I understand correctly, they use a pre-trained BERT model here that is like off the shelf. They don't use any new domain specific. It's not like they retrain on their data sets, right? So it's as zero shot or as clean as they can. In principle. Exactly.
They call it a small 8-layer BERT model. So something just under BERT base.
Yeah. I mean, I think that's intuitively, it should make a lot of sense, right? If this embedding space is somewhat semantically relevant, probably like the optimal way to encode is this sort of tree-like going into more and more fine-grained differentiation, and then you get this path. In practical terms, they use, I think, 10 clusters, right?
They start with 10 clusters, and those give them 0 to 9 for the first digit, but then they cluster recursively within each of these.
But this sort of, if you get 10 clusters, this sort of nicely results in one digit at a time, like 0 to 9, that identifies each one of them. So it kind of naturally translates into decimal thing, right?
Right.
Or at least that's how I understand.
Yeah. So if you look at the ID, you can understand what cluster the document was ultimately in, because reading it from left to right, it tells you the path.
Okay. So you might think that this will work the best across the board, but might not be that way, as we'll see. But before we jump into the results, let's talk about this differentiation between unsupervised pre-training and which leads to zero-shot sort of testing of the model versus fine-tuning on these.
Yeah. So we've talked about two of these training tasks, I guess we'll call them, right? So one is mapping document ID and document, establishing that mapping, and the other is teaching some way to, given a query, predict the doc ID. So I think their ideal setup is a multitask setup where they, in some proportion, use both of these. So during training, sometimes it's document to document ID, and sometimes it's query to document ID. I think the former is 32 times more common, if I read a later figure correctly, but it's some mixture like this, where they more often do the first task. This is the supervised setting. And then the zero-shot setting is just not using the second task. So they don't include this task of going from query to document ID. They skip that. Because this requires labeled data, right? It requires labels of what document is relevant. They assume they don't have it.
Which I think is really interesting, right? Because if you are to go back to what we have mentioned before, if you look at some classical method like BM25, when you index a corpus using BM25, you don't need any label data. You only the corpus statistics are enough to index that data. So kind of conceptually, to me, it makes a lot of sense that you would try to index a corpus only looking at the corpus, so to speak, right?
Yeah.
Which is only pre-trained and supervised, or at least sort of equivalent in some way.
Right. No, yeah. Ideally, you wouldn't have needed to see the corpus before to index it. Yeah. I guess even with BM25, you need to identify tokens in some way, but this is unsupervised. You ultimately need to know what tokens exist in the corpus so that you can...
you can make statistics and counts. And all right. So I think we can... Let's first explain very quickly the data sets that they use, the metrics, the baselines, and that's it.
Yeah, so the data set is this natural questions. This is, unsurprisingly, a natural question that's related to a Wikipedia passage. And then there's one relevant document for that question. It's a Wikipedia passage. This is crowdsourced, where I think crowd workers came up with the questions. As far as implementation details, they're starting from pre-trained T5 models, going up in size from the base model to the extra large model. This is going from, I think, 200 million to 11 billion parameters, it looks like, so big range there. And then as a baseline, they use T5 as a dual encoder. So for this distance retrieval approach, where it's querying document representations, it's indexing the document representations, and then there's some approximate nearest neighbor search to
so
find
like
them.
dense retrieval step. And they also use different partitions, right, of the natural questions dataset. I don't think they use the full set, but they use the 10K.
Yeah, so I guess they want to look at how the size of the data set affects performance. So they go up to the full data set, I believe, which is they call 320K. So there's 320,000. It's the number of trained pairs plus the number of validation pairs. So I think the important thing is 320 is the full data set, and they look at subsets.
Yep.
So they look at a subset with 100,000, so 80,000 trained, 20,000 validation, and then a 10,000 subset, which is just dividing those numbers by 10. 8,000 trained, 2,000 validation.
So you mentioned to me offline that that it would have been nice if we had seen these on some other data set. What is your impression why they used natural questions and not some MS Marco or something that we've talked about a lot?
So one issue with MS Marco is it's about 8.8 million passages. This is way, way larger than they're looking at here. So their number of documents in the full collection is around 230K, right? So it's 40 times or so to go to the full MS Marco size. And you can anticipate there has to be capacity issues at some point somewhere. So I think just for the sake of demonstrating that this can work, it makes sense to start with something reasonably sized. I guess the downside of that is there's a lot of research on MS Marco that's nice to compare to use for context. But I understand why they would use natural questions here. It makes the experiments possible.
You said, it makes a lot of sense from this perspective of this is... this performs pretty well, but it's more of a proof of concept that this is like a reasonable thing to do or that works pretty well, not necessarily that it's, state of the art or something like that.
Yeah.
All right. So then I think that we can just jump into the actual numbers, the experiments, the results. So table 3.
Yeah.
I guess it's the first big... there's a lot of numbers here.
Yeah.
So where do we start?
This is a fun table to characterize with audio only, actually. So, of course, remember they're doing this on 3 subsets. So we have 3 columns dealing with 3 subsets. And they're also calculating the metric 2 different ways. I don't know, actually, if we described what metric they're using here.
Oh, actually,
I think we didn't. Yeah, so they're using hits at n. So what this means, so hits at 1, for example, is how many queries have the correct answer in the top 1 documents, right? So this is 1, or if you normalize it, it's 1 if your system is perfect. Hits at 10 would be, if you look at the top 10 documents, how many queries have the correct answer in that top 10. I believe there's only 1 correct answer per query because of how this is constructed.
That would make sense,
Yeah. So those are the metrics. So just some general trends. I think that the task gets harder as the size of the data set increases. So if we look at, for example, the largest model, so this extra large model, we look at, say, hits at 10, and we look at atomic doc IDs. So you see this is a lot going on in the table. But if we look at those, what we see is that we go from 77 is the hits at 10 with the smallest subset, down to 68 with the middle subset, down to 55 with the larger subset. So I guess the queries are changing here too. So you could argue that this is some of the effect, but it seems like to me that increasing the size of the collection makes things a bit harder, which to me is intuitive because it has to be stored, right?
Yeah. I guess that I don't know if that's something I'm getting ahead of, but that is interesting to look at is whether the model size, how is the interaction between model size and corpus size scaling, as in a small model should be big enough to memorize a small corpus but not a big one, whereas a big one should be better across the board, right? And we do see that the larger models always perform the smaller ones.
Yeah, there seems to be no real advantage to using a smaller model here. I think we won't mention numbers for all of them, but just for reference, there's 4 model sizes, like 250 million, 800 million, 3 billion, and 11 billion. And using the larger model always seems better. There's not as much of a clear winner, I think, in terms of how to represent the doc IDs. So we talked about these 3 strategies: the atomic, where it's a token; the string doc ID, where it's a bunch of individual characters; and the semantic one. Depending on where you look, the best results change. So the semantic approach is the best for hits at 1 on 2 of the subsets. The string approach is the best for hits at 10 and hits at 1 on 2 different subsets again, and then the atomic is the best for a single subset. And somehow I'm missing the 6th best here. Oh, sorry. So the string is actually the best 3 times. But the point
yes.
I guess I want to make by saying that is that the best strategy varies depending on the metric you're looking at and the size of the corpus.
There's no such a clear winner, right?
Yeah.
Which I think it's to a degree surprising, right? You would expect. Well, I mean, the semantic string doc ID makes some intuitive sense in this way of like it should be some semantically relevant ID, but it seems to not always perform best, even in these not in the smallest partition of the dataset, but in the middle one, which is kind of surprising to me. I don't know. Something else that is also surprising to me a bit is if you look at the performances of the atomic doc ID for all of their sizes, they seem to be a little bit all over the place, as in sometimes making the model larger will hurt performance. Right, if you look at, for instance, at hits at 1 for the NQ100K for the atomic ID, the performance for the base model is 23%, and then it drops to 17 and 19 for slightly larger models. And I think that the authors mentioned that they have some stability challenges, or apparently it's pretty hard to train this layer that is so large. But at the same time, this sort of begs the question, if this sort of stability, probably these numbers are not, so to speak, are not the perfect optimization of the neural network, because there's a lot of practical challenges to doing that. So my sort of question that this makes me wonder is, imagine there was a way to make sure that this training was stable and that this could be trained in a more stable way. Maybe the most naive assumption for representing documents would outperform the rest of them all of the time. I mean, I'm just
it's possible. Yeah, I mean, I especially compared to the naive string doc ID approach, where you generate it 1 token at a time, it seems much. I mean, this is just an optimization to simplify the model, I think. But I can't think of to me, intuitively, I don't see why this approach should ever be better in terms of effectiveness, in terms of ranking metrics, right?
Yeah.
It's way better probably for efficiency, because you don't need to learn all these outputs. But setting that aside, I tend to agree with you. I think I could imagine a world where atomic doc ID is better than that with perfect optimization. But, I say imagine, clearly.
Yeah, of course. But still, I kind of find it hard to wrap my head around this idea that the model would just learn 1 separate token for each document and that's it. I don't know. It just I find it kind of imagine a classification layer that's just 100 like 3. I mean, he's literally 300,000 in size.
No, so here, it's 300,000, and their vocab, I believe it's around 30,033 to start with. So you've increased it by 10 times in order to store the document ID tokens. It's very extreme.
Yeah. Anyway, so at least to me, the big takeaway is semantic string doc ID does seem to perform best in the large large corpus, large model case, but it's not a very clear-cut thing, and it's unclear to what degree things could be optimized further and the results would change based on that. One thing that I would like to ask you is they use as a baseline BM25 and T5, but they also have their own optimization of that. Is there any way that we can know how competitive this is compared to other methods? How much they push this T5 baseline? To get a sense of how close this is to state of the art or to other methods that we have talked about.
Yeah, I don't have a great idea of it, but from what I've seen, I think this T5 baseline is from some recent paper where they use T5 as an encoder. That paper didn't have a good ranking comparison on, for example, MS Marco, from what I remember. So it's not that easy to put it in context. My sense was that maybe it could be optimized a bit more, trying to compare natural questions numbers from different places. But this is always really hard to compare across papers because there could be parts of the experimental setting that either I missed in the paper or weren't stated in the paper. And without, rerunning the experiment yourself with, the code and so on, so I'm a bit hesitant. But to me, I think maybe their T5 baseline may not be as strong as some of the dual encoders like ANTs, for example, that are using these hard negatives in order to improve training.
Yeah.
My initial sense.
My impression is that so much of this performance relies on a lot of these small tricks and small optimizations, like choosing very carefully negative samples and all of this stuff. So I wonder how that...
I guess we could say with BERT-based encoders and other encoders, it is very important to do this hard negative mining, or it seems to be important. There's different ways to do it, but it always improves. And based on the fact they're not doing it here, we either have to say that this could be improved, or for some reason it's not needed with T5, I suppose. I tend to think it would still be needed with T5. I don't see a reason that hard negatives would no longer be important. But again, this is speculation.
It makes sense. All right. So far we have talked about results that are fine-tuned, right?
Yeah.
And right below we have the table 4, which is a slightly smaller table with the zero-shot results, right? So basically using this model without labeled data to do retrieval on the same three sort of partitions of the data set.
Right, which means they don't have these query pairs, so they're never feeding the query document ID pairs during training.
Exactly. So there's a pretty big domain shift you would kind of conceptualize between mapping document content to ID versus mapping query to ID, and you're sort of seeing how well this shift, how well the model transfers between these two modes. Or would you think that's a good characterization of what's going on conceptually?
Yeah, I think so. I mean, the way I'm thinking of it, they're essentially treating their query as another document and hoping the query is in some way similar enough to the right document that it spits out the right document ID. Is how I'm conceptualizing it. Yeah, I think. But
I mean, the reason I'm sort of stressing that is my understanding is that with unsupervised pre-training, that doesn't work that well, right? When you have zero, I mean, we talked about this previously, right? How hard it is to use zero labels, and how that transfer is not that good in the conventional dense retrieval setting.
Yeah, that's right. So the paper we looked at last time, for example, Spider, was a pre-training task along these lines. So it's not at all trivial to come up with any sort of unsupervised task like this that works well for retrieval. So I think we should give them credit for this. Their task works pretty well here. So if we look at like the smallest subset, it performs a bit worse than in the supervised setting. So something like going from about 48.5 hits at 1 to 44. So it's a drop, but it's still really high. It's higher than BM25, and it's not failing at all on that smallest subset if we look at the best results. But things get a bit worse as you increase the size. I'm not entirely sure why. So if we look at the middle subset, now we're in BM25 territory already. We're better, but we're much closer to BM25 than to the previous.
Yeah, so I guess that the worrying or the interesting part is that BM25 is pretty consistent across the board with when it comes to hits at 10, for instance, right?
Yeah.
Whereas...
Yeah, but actually, let me slightly amend that. I think we're about halfway in between their previous performance and BM25. So maybe it's not fair to say it's BM25 territory, but they've lost something like half of the gains. So like BM25 is 21. Previously, it was at 27.5, and now they're at 23. So it's still working to some amount.
Something that I'm just now realizing that I don't quite understand is how could it be that the hits at 10 for the smallest data set versus for the 100, the middle data set for BM25. Why would the results be better on the larger data set? Shouldn't they be sort of monotonically harder as there's more documents?
There are more documents, but the queries and documents are both changing. So I think it depends on this also.
Okay.
Yeah.
So you cannot really do apples to apples.
Yeah, which makes these comparisons with sizes a bit harder, right? Because we're looking at different queries. We have to remember.
What I was.
It might be interesting to have like a minimal query subset evaluated on all three, but
Anyway, yeah, but I would say that it's pretty impressive, right? I mean, to me, it seems pretty good zero shot transfer, and it's promising in this in this mode where it's clearly outperforming BM25 in these data sets with, like I said, using zero labeled data. So
yeah, no, it is. And I mean, even for the largest subset, it's still somewhere in the middle between fully supervised and BM25, I would say, I think is a fair.
So the last thing that I think is interesting about these zero-shot experiments is now what document ID representations are leading, because we find something quite interesting, right? Where we see that the semantic string doc IDs don't perform that well across the board, right?
Yeah, so for the smallest subset, the atomic, for whatever reason, don't work so well. They're a bit worse, but the naive string and the semantic string both work. But then for the medium and the largest subset, the atomic is significantly better. So when I was making these BM25 comparisons, it's with the atomic. If we look at the others, we're worse than BM25, actually.
Yeah, but I'm just quite surprised at the variance. For instance, the semantic string doc ID seems to fail quite strongly, right? We're talking, for instance, a difference in performance from 26% to 57% between the semantic string doc ID versus atomic doc ID, which is almost like literally, it's more than double.
Yeah,
it's quite. It sounds. I don't know. Would you have any intuitive thinking of why that could be?
No, this was very unclear to me. I mean, this is more complicated, right? They're doing this clustering. There's something about, cluster membership topics happening in the doc ID, or, this is reflected in it to some extent. But why this doesn't work zero shot, I'm unsure what's changing here. It could be that the queries are actually helpful for understanding this mapping. I don't know. Maybe the queries help discriminate documents because the document is relevant to one query. But I'm not, I'm unsure.
I guess what I'm wondering is, again, to what degree this difference might come down to some optimization artifact or to some failure mode that, that they weren't able to sort of overcome or something in these lines. Because some of these numbers are surprisingly low, I would say, in some cases, for no apparent reason, right?
Semantic string is just totally failing on the two larger subsets. There's some optimization issue, but I don't know.
I guess further research is certainly required.
That's not the last paper on this topic.
No. Okay, so do you want to talk about any other kind of results before we jump into the kind of last part, discussion, future work, applications, where we can brainstorm a little bit about those topics?
Yeah, just really briefly, I have a couple notes. One is we were talking about these strategies for learning the document ID to document mapping. And we said back then that inputs to target, so the one where you take the document text and then you predict the document ID, was working best. They also mentioned that bidirectional is only slightly worse, and then the other strategies just fail.
Okay.
So the span corruption doesn't work, and the reverse doesn't work, where you predict the document from the doc ID. I think is a little interesting. The other thing that I thought was worth pointing out is this difference in document representations that they index. So we've been talking about what they call the direct, which is just take the first L tokens from a document.
Yes.
But they also have a plot where they look at the different ones, and it's kind of a similar case. So if you take the first 32 tokens or the first 64 tokens, everything seems okay. But if you increase that too much, if you take the first 128, you take a really big performance hit. I print this really small, but it's something like going from 22 hits at 1 to 13 or 14 hits at 1, very roughly, like a big performance hit.
Yeah, that's certainly super interesting. We're talking about figure 4, where if you have the paper in front of you. But it is a really substantial difference, right? For a context that in other contexts would not be that large, right? 128 tokens is not...
it's very manageable.
It's very manageable in a lot of other contexts, yeah.
Yeah. But maybe something about how, using the model as a way to store the documents makes this harder, right? You do have 4 times as much to store with going from 32 to 128.
Yeah. Yeah, absolutely. I mean, there's all these, with this method, there's this whole sort of universe of efficiency and scaling things that we don't know and don't have intuitions about, because it's a pretty new way of doing retrieval. So yeah, a lot of these things are hard to make sense of, at least in my in my head.
It is. So also, if there was also the chunk approach, remember? So rather than the direct index, they call it, I think, inverted index, which means they chunk documents into sizes of L and index these. So this with 32 actually also doesn't work. So here, remember, we started off with hits around 22 or so. With this approach, it drops down to 5. So it's much worse than even a direct index with 128 tokens. I'm not entirely sure what's going in there. My understanding was that a document can have multiple chunks. It's not a one-to-one mapping. Maybe this makes it harder to find like common terms and topics and commonalities within that document to store it. But I don't know.
No, it's hard to find reasons for these things. But super interestingly, these decisions make I've already said it, but these decisions, design decisions, make a huge difference. Like the difference of something that's worth publishable and something that's not even that. So, I'm super interested in seeing where other people take this further, because I see so many ways that this can be sort of explored further or applied to other data sets and all of this. So shall we talk about that, or is there anything else?
No, I think there's nothing else.
I guess that... a very good example of I've talked to a few colleagues about this paper, and pretty much always the first question is like, but what do you do when you want to add a document to the to the corpus?
You maybe change your paradigm. I don't know.
And the answer is you don't.
You ask why you needed to do that.
So I guess like the main first obvious drawback of this system is like you need to pretty much train a whole model with one corpus that should be static, and you cannot just decide to add one document, right, to your corpus.
Yeah.
Just like that. Which seems like a pretty big drawback to me.
Just to be clear, you can imagine ways to add it, but they're not guaranteed to work, I think, is part of the issue, right? You could run a training step with the new document, but if you run it too often, maybe it forgets old document. It's really unclear what to do here. There's no clean answer, I think.
Exactly, yes.
Especially with atomic doc IDs, because now your vocab is growing also. Exactly.
You just like adding one. But I don't know. I mean, what I was thinking about is, okay, this sort of approach certainly cannot scale and work for applications where you have indexes that are constantly changing. Like, I don't know, you're constantly getting news coming in. Web search, of course, like super relevant. Like, you need to be adding documents all the time. But there's other applications where you might want to search within a closed corpus that is pretty much static, or it only changes maybe once every month or something like that. So it becomes more manageable. So what do you think about, do you think that this is something that could become a thing in those contexts? Do you, I don't know, what are your thoughts? Is there like a space of applications where this could become a thing, or is it too out there idea?
Yeah, I mean, I'm not exactly sure what the application is, but I think this is the most interesting use case that I've thought of, as you mentioned, right? So you have some small high quality corpus like Wikipedia. I don't know if you can call that small, like an encyclopedia, right? Mm-hmm. And you have some use case where you want to search this, and in your use case, it's nice to be able to just move the transformer around. It could integrate well with other things. It would still be differentiable. The fact that you're outputting document IDs, though, it depends. It doesn't necessarily integrate easily into some larger architecture.
Yeah.
But this is where I think of the sweet spot, at least so far for it, right? Some high quality, smallish corpus that's really useful to somehow query. Mm-hmm. You can even imagine like one of these medical, like Mayo Clinic or WebMD, or one of these like medical resources that are, very high quality. They're really careful about what they put there.
Yes.
Maybe as a way of interacting with something like this. Yeah. I mean, this also raises the question of if you're using a corpus like that, you want the answers to be right. But this is, a separate issue.
Yeah.
You're raising the stakes if you create, I don't know, if you call this like a single unit that you want to pass around, you're in some ways raising the stakes for how well it performs, because everyone is just going to use it like a black box. There are no other moving components.
Yeah, that's, I guess, one other big drawback that is shared with other neural retrieval models, right? Which is the interpretability part, which, in BM25 and statistical-based models, you can pretty much understand why documents are retrieved, and you have some formal guarantees on what garbage is not going to pop up. But again, these models probably more susceptible to all kinds of really weird retrieval failure modes that are hard to understand. It's hard to prevent, or hard to understand. So, but in that sense, it's not that much different from the existing dense retrieval or cross encoders.
No. In terms of failure modes, I think it's not necessarily different. I was thinking maybe if you have like a use case where you're concerned with this high quality resource, perhaps the failure modes become more important. It was what I was thinking. But you're right. The failure modes that exist for dual encoders, I think, also exist here. It's not so different.
And the fact that they're not not human interpretable,
right.
or of this.
Right.
Another sort of big drawback that I had written here is the memory efficiency or scalability of this system, right? I mean, we're talking here, this model is 11 billion parameters. I think that this is around a few dozen gigabytes, right? If you store it,
it's 32-bit floats,
as 32-bit floats, and don't do any more optimization. You probably would need even larger models for larger. I don't know. It doesn't seem like a very efficient way of storing things. Do you think that this is solvable by some optimizations like pruning, quantization, of these sort of techniques? Or do you think maybe this is more of a fundamental efficiency problem of this approach more fundamentally that will make it hard to?
Yeah, I can see arguments in both ways. So if we think about like the pruning, stuff like that, this will reduce the model size. But you could say as your collection grows, you need a bigger model still because you have more to store in it. However, you could also say that as your collection grows, that the model may be able to pick up on more common things, for lack of a better word, between the documents you're storing. So maybe it's not a constant storage cost every time you add a document, right? Maybe at some point it knows most of Wikipedia, and so you add this new news event, and it's not storing something entirely new. It can be stored in terms of other things that have been stored in some way. But you see how hand-wavy this is, and I don't know which way.
Yeah, but in some intuitive sense, it makes sense. As in, if you again make the human analogy, which has a lot of problems, but still, if I kind of show you, the latest paper that came out from whatever group, you have so much knowledge about it that you will just eyeball it, find a few points of interest, and you have incorporated that knowledge without having to sort of memorize that many things, right? You will kind of be able to pull in all of this existing knowledge. So in some, if this can be somewhat analogous to this process, intuitively it makes sense that the sort of effort it takes to add documents should be sort of have should not increase linearly, but should sort of plateau a little bit, or
at some point to some degree, but I don't know what the values for either of those are.
Said. Absolutely. But still, I think it's,
Also, the doc IDs have to be stored. I'm not entirely sure how to make sense of that. I think this is something new we have to store with every document, assuming they're not semantically meaningful. If they are semantically meaningful, it's unclear to me how much this improves things.
I mean, that's another big question that I have indeed. In this paper, they they sort of constrain themselves to looking into non-semantically relevant doc IDs, right? Pretty much numbers like strings, or almost, not random, but almost just IDs. But you could conceptualize a way in which you assign some semantically relevant ID to each document, like its title, for instance.
Yeah. So
to say something,
even beyond the clustering, you mean?
Exactly. And just instead of representing a document as 10 digits, you have the bag of words, I think you've mentioned before, or you get, if documents have title, maybe the titles are unique, and that's good enough, and you just autoregressively generate the title, or you can just get some top words, or you can just train. I think you've mentioned something before.
Yeah, when we were talking before, I mentioned doc to query. So I was trying to think of what I would use to come up with some terms to characterize the document. So there's this model, it's also built on T5, doc to query, where the input is a document, and then it tries to predict a query that document would have been relevant to.
Okay, yeah.
So you could run this, get 3 or 5 queries, and maybe do a set thing to give a set of terms that characterizes the document. I don't know if that would be ideal or not. I'm just trying to think of how. Yeah.
It's a reasonable thing to try. At least it seems to me, and maybe in this sense you would have the added benefit that you could have some sort of zero-shot performance in a way that so. I don't know if this will be clear, but if you have trained on a training set that only have a fixed set of documents, but then you want to retrieve a new document that wasn't in that, then, the autoregressive generation of the identifier will be constrained to some beam search. And if you just add this new document ID to the sort of dictionary of allowed document IDs or something, the model will sort of output that ID maybe in a zero-shot manner, and that will have a high likelihood, and it could be ranked theoretically without seeing that document before.
Yeah.
There's a lot of ifs.
No, but I definitely see the process. Yeah. I think the intuition is something like, if you can find the 10 top salient terms from a document, this will work for any new document you add. You can always find the top salient terms. The model can find them, you can find them, and you both agree on what they are. Mm-hmm. But I don't know how this interacts with training or beam search or anything like this also.
Yeah.
It's even the ordering of these terms, I'm not really sure what to say about it, especially if you're using teacher forcing. And
you might have some problems enforcing uniqueness in these terms as you add, right? Because as you add documents to a collection, two documents might be similar in ways that, they're not necessarily unique. Yeah. But still, I'm still really looking forward to other works that explore these in these directions. One of the, I'm guessing also, I don't know, I don't think they studied this in any depth, but the issue of efficiency of inference, how fast this thing can run, pretty much.
I don't think they report that anywhere. But I think... So I think that it's mainly a property of the underlying T5 model they're using here, because they're not changing the number of parameters. I guess it would be a property of which T5 model they use, and then how long the input query is, and whether the output is one or more tokens. Because if it's more tokens, it requires several steps.
Yeah, exactly. So what I was thinking is if sometimes in these autoregressive things generation, they use pretty large beam search, right? Where you actually calculate like a very large tree of possible and then only kind of keep the highest likelihood paths, so to speak. And that my understanding is that is very computationally expensive. So I don't know if they are doing any of that here. Actually,
I think the naive string decoding, they do some kind of top K beam search.
Okay. Okay. So yeah, my guess is that could have some sort of latency or performance issues, which are pretty relevant in the context of like applicability of these things to common applications, like products, commercial.
Yeah, I don't think it's an extremely fast model, but it is just one model. They've eliminated other steps, so there's some benefit there.
Do you have any other points that you would like to raise?
No, I think no final points. Maybe one quick observation. You proposed using the titles as a way to store the document IDs, the title as a document ID. And I was just realizing this is exactly what this autoregressive entity linking that we were talking about at the beginning does.
Pretty much.
So it would be interesting to try, right? Maybe there are similar patterns that you could take advantage of there. I would be curious to know how well that works. I
mean, it's super interesting because in that case, the task is framed as an entity linking task, not a retrieval task. But they share a lot of connections. I mean, conceptually, it's pretty much the same.
Yeah. The flavor of the approach is quite similar, yeah.
So that's super interesting. Yeah. Anyway, like I said, I really like this work, and I mostly like sort of doors that it opens for other people to build on. I'm really also looking forward to seeing how these results compare more heads-to-heads on maybe, I mean, like you said, MS Marco probably is too big, right, for this, but you could have some smaller partition maybe of MS Marco or
that's true.
Something like that.
Yeah, or if you're looking at a zero-shot setting, something like Robusto 4, like a much older data set that's around 500,000 documents, very thoroughly judged queries, but not many of them. There would be a way, I guess, to find another smallish data set. But yeah, I'm excited to see what people do with it. It's a very interesting new way to look at this.
All right. So I think that brings us to the end. Thank you for listening and joining us. And we'll see you in the next episode.